The second conic we'll talk about in this section is hyperbolas. Again, there's a link right here I would like you to click on. It's in the portal page, and it'll direct you to this page right now. So you'll see hyperbola interactive graphs. And so if you just scroll down, it gives you a couple of interactive things. And you'll notice that this is what the graph of a hyperbola looks like. And obviously it will change based on where these 2 points. Again, just like an ellipse, a hyperbola has 2 foci. But it's a little bit different because instead of the sum of the 2 numbers, what happens is it's actually the subtraction of them. So if you see that PA, meaning the point, is 3 units, then PB will be 1 unit. So from here to here is 3, here to here is 2, or I'm sorry, 1, so the subtraction will be 2. And as I move that along, they both increase. And I know that kind of fluctuates between 1.9 and 2, but it's kind of rounding that or estimating that right there. And it's kind of the subtraction of the 2 to make sure it's the same distance. Now even if I hop over to the top part of the hyperbola, you'll notice the same thing. It's the subtraction from the 2 that give you that distance of about 1.9. And again, if you remember in class, I kind of talk about how a hyperbola is kind of the vertical split down the 2 cones. So if you need to look at your book for a visual of that, I'd kind of go for that. You can also kind of move Q to see how the hyperbolas can get narrower or wider. And one thing that you should kind of see is, you see how these have asymptotes? And we'll talk about that in just a couple minutes when we start graphing. If you scroll down, there's just a couple of other things too. Just like parabolas going left, right, up, and down, hyperbolas can do the same thing. So go ahead and change those around, play around with it. Look at the asymptotes. So our definition of a hyperbola is a set of points in a plane such that the absolute value of the difference of the distance from 2 fixed points is constant. And that's why if you look at the equation, it's the subtraction, because remember, it's the difference when you actually go to graph it. And just like the ellipse, it's going to be equal to 1. Now again, we're going to start by looking at hyperbolas that have center 0, 0, and you can kind of tell that because if you look at the numerator, there's no other numbers up there. A and B kind of act very similar, but this right here is going to be a hyperbola that opens up and down. So it won't necessarily have x-intercepts. Sorry, this is a parabola that opens left and right, so it won't have y-intercepts, but just x-intercepts. This right here is an equation of a hyperbola that will be opening up and down. And since it opens up and down, it is just going to have y-intercepts and no x-intercepts. There should actually be a squared right there. And finally, if we look at the equations that have center HK, very similar to what we talked about with the ellipse and then the basics with the center 0, 0. The first one, because it has y in front, will be an ellipse that opens up and down. The second one, because it has an x in front, will be opening side to side. And again, I apologize, this should be a squared underneath. So how do we graph these? Well, let's look at the first example and kind of talk our way through this. In the first example, we have x squared over 4 minus y squared over 9 equals 1. So there's a few things we want to identify. First of all, we want to identify that our center is 0, 0. We'll identify that A is 2 and that B is 3. We also want to identify that this is going to be opening left and right, and that's because of the x squared right there. So this is what you're going to do. And these are really going to be just rough sketches of the hyperbolas. They're not going to be anything exactly perfect. We're going to start with our center. We're going to go to 0, 0. And because the A is over the X, we're going to go vertical 2 spaces and kind of put a dashed line. And then we're going to go left and put another dashed line. And that will kind of be the beginning points of where the hyperbolas start to branch out and left and right. The next part, what we're going to do is we're going to go up 3 and make another dashed and down 3. And hopefully what you notice is that once we put those dashes in there, it kind of forms a little box. And what these boxes do is they actually create the asymptotes of which the hyperbolas kind of move to. So I'm going to try to make this as exact as possible. It's a little hard on the laptop. So you're going to want a ruler to do this. So I'm going to create 2 diagonals just through the corners of the boxes. There's 1, and then there's another. And you should be able to tell where the corners are kind of based on how many you went over. So we went over 2, up 3. So an example, this point right here would be 2, 3. This over here would be negative 2, 3, and so on. And what happens is that we're going to use that as a guide for our hyperbolas. And the starting point of the hyperbola is on the box at that point, and it just kind of flows out towards our asymptotes. And because it's starting with an X, it'll go open left and right. And so the box and the asymptotes are really not part of the hyperbola, just the green part. And again, it's not going to be perfect. It's just a rough line showing that the graph approaches the asymptotes but never touches. If we take a look at example number 2, we have 9y squared minus 16x squared equals 44. And very similar to what we talked about in the ellipse, it needs to be equal to 1. So what we're going to do is we're going to divide by 144 to all parts. So that creates the equation in the format that we're used to. Again, a couple of things that you're going to kind of note right away. First of all, we're going to start with our center at 0, 0. B will be 4. A will be 3. And we're going to, because it starts with a Y, we know it's going to open up and down. So we're going to start with the center, and we're going to create the center at 0, 0, and we're going to count up 4, 1, 2, 3, 4, because that's B, and down 4, and then left 3, right 3, and that's just going to create a box for us to follow to create our asymptotes. So you're just going to take a ruler, or your ID, and you are going to create the asymptotes. Again, because this is because this starts with a Y, the hyperbola will go up. So there's the center of that first one. And again, I'm just going to try to approach those asymptotes on the side, and you can kind of see how it forms the hyperbola. Again, nothing else is really the hyperbola, just the green. And now for our last example. You can look at this and you can see it's a little bit different than what we've talked about because of a few things. One, you can tell that this has a different center. The center will be negative 2, 4. And you'll also notice that this doesn't have a fraction. Well, that's an easy remedy. Since it's already set equal to 1, we don't have to worry about that. What we can do is we can just make this 1 squared. So our A will be 3, and our B will be 1. So now in this case, though, what we're going to do is we're going to start at the center, -2, 4. A is our horizontal, so I'm going to count 1, 2, 3. 1, 2, 3. And then B's are vertical, go over 1, up, run. And you can again see the box that it forms. You're going to draw the diagonals. And because this starts with an X right here, that implies that it's going to open side to side. So when we go to graph this, I'm going to go to the side ones, and we're just going to have it flow out to both sides.